This video is going to be on thermodynamics. We'll start with a little quote from Homer Simpson. Not too often you get a Homer Simpson quote in chemistry, but in this house the laws of thermodynamics will be obeyed, and that's what this video is on, thermodynamics. First, a few definitions. Those reactions which release energy in the form of heat are called exothermic reactions. Here the reactants change to the products and they release heat, so heat is on the product side. And because heat is on the product side, the reactants have more energy than the products. If we look at the equation, the amount of heat in the reactants equals the heat in the products plus an additional amount of heat. And so it's kind of like the energy starts off here and then ends up down here. The pathway goes something like this. So the reactants are higher than the products. So there's a net loss of energy. The energy goes from higher to lower, and therefore we consider this a negative change. A negative change in enthalpy indicates that the products have less energy than the reactants. So when you calculate the change, it's the final state minus the initial state, a smaller number minus a larger number, gives you a negative value. And of course, the total amount of heat in the universe remains constant, so the amount of heat is the same. And so if we go back here, the amount of heat in the universe is the same, but the amount of heat in the products is lower than the heat in the reactants, because some of that heat then is lost to the environment. And the opposite of exothermic reactions are endothermic reactions. These reactions absorb heat. So now the reactants absorb heat to become the products. And so now the reactants are at a lower energy level. The products are at a higher energy level. Reaction progress goes something like this. So there's a net gain of energy, and therefore the change in enthalpy is considered to be a positive. So we have a positive change in enthalpy. There's more heat in the products than in the reactants. Here the energy from the universe is absorbed into the reaction. So again, the amount of energy in the universe is constant, but now there's more energy stored in the products than in the reactants. We can write these types of reactions in chemical equations, but if we add the heat to them, they become what we call thermochemical equations, equations that indicate the amount of heat absorbed or released in a chemical reaction. So if we look at these two equations in the box, the second one represents a regular chemical equation, reactants changing into products, no information about heat is given. A is a thermochemical equation because now we have reactants, we have products, plus we have information about heat. In this case, it is an exothermic reaction. Units of heat energy include the SI unit, the joule, the calorie, which is the amount of heat needed to raise 1 gram of water by 1 Celsius degree. So if I have 1 gram of water at 20 degrees Celsius, I change it to 21 degrees Celsius. That is going to take 1 calories worth of heat to raise that by 1 degree Celsius. And typically when we hear about calories, we think of food calories. Food calories should always be spelled with a capital C, and it is equivalent to 1,000 calories or a kilocalorie. So food calorie is really a kilocalorie. The rest of this is just going to be on stoichiometry, and if you understood stoichiometry, this is just another variation of that. We've gone from particles to moles to mass. We've gone from particles to moles to liters, liters to moles to mass. Now we're just going to involve energy. Same kind of calculation. Most of our calculations are going to be on this axis. I will either give you a certain number of grams, ask you for a certain number of kilojoules. So you go grams to moles from the periodic table, moles to energy given the enthalpy for a particular reaction. And we can go the other way too. I can give you a certain number of kilojoules. You can calculate to moles, then calculate to grams. And so that is what we will be doing here. Sample problem. We're told that sulfur trioxide gas in the air reacts with water vapor to form aqueous sulfuric acid. So we can write a thermochemical equation for this. And we're told that for every 1 mole of water, This is the enthalpy change. So we can write it in the reaction like this, or we can write it as the change in enthalpy equals, in this case, a negative 129.6, since it's an exothermic reaction, the energy being released. So we wrote the thermochemical equation, and now we're asked if we have 800 grams of sulfur trioxide, how many kilojoules are going to be released? So we have to go from grams to moles and then to kilojoules. Note there's this many kilojoules for 1 mole of the SO3. So grams to moles, just using the periodic table. So grams and grams will cancel. And then again, for every 1 mole of the SO3, there's 129.6 kilojoules of energy released. Note we're not carrying the negative sign here because we just want to know the quantity, and that then equals 1,295 kilojoules. Moles of SO3 canceling out. So again, pretty simple calculation, grams to moles to kilojoules. Try another one. We have 21.95 kilojoules of energy are added to 1 mole of carbon dioxide. Note the ratio. There's 21.95 kilojoules for 1 mole. When I write the balanced chemical equation from this point on, we need 2 moles of carbon dioxide, so we need 2 times that 21.95. And since the energy is added, this is an endothermic reaction, we write the energy on the reactant side. So that is the balanced thermochemical equation, and the change in enthalpy then is positive. So there's this many kilojoules per 2 moles of the carbon dioxide, 2 moles of the carbon monoxide, and per 1 mole of the oxygen. The question asks for 100 grams of carbon dioxide, how many kilojoules of energy are going to be released? So it's grams to moles to kilojoules. So 100 grams of carbon dioxide, 1 mole for every 44.01 grams. And then again, there's 43.9 kilojoules for every 2 moles. I could have put in 21.95 kilojoules for every 1 mole as well. Both those would have given me the correct answer of 49.88 kilojoules. Last sample problem, we're told the enthalpy change for the combustion of hexane is C6H14 is 8,326 kilojoules for the balanced reaction. And so write a balanced thermochemical equation. So here is the chemical equation. Again, the change in enthalpy for this one is going to be a negative 8,326.0 kilojoules, and that's going to be per 2 moles of the hexane. And so we want to find out how many grams of hexane must be burned to furnish 5.2 times 10 to the 7th joules. Since the enthalpy is given in kilojoules, we're first going to convert our 5.2 times 10 to the 7th joules into kilojoules. So we divide by 10 to the 3rd, or just subtract 3 from 7 to get 10 to the 4th. And 1 mole of hexane is equivalent to 86.20 grams. And so we start with the given 5.2 times 10 to the 4th kilojoules. We're going to go from kilojoules to moles to grams. And so we're just doing the same problem backward. We're starting with kilojoules. We want to end up with grams. So we'll go kilojoules to moles to grams. So kilojoules to moles, again, for every 2 moles of the hexane, there is that amount of energy being released. Again, we're skipping the negative sign. So now kilojoules and kilojoules will cancel. And then we want to convert to grams. Now this problem, we got to go one step further because we're told it's 80% efficient. So out of every 1 unit, we're only getting 80%, or out of every 1, we're only getting 0.80. And so now we have to divide by 0.80 because we really need more than the exact amount as if we were getting 100%. So it comes out to 1,350 grams, or 1.35 kilograms. Hope this helps.